waveforms, spectra and bandwidth. Here we have some axes showing how voltage in millivolts changes with time in seconds. We can add a wave to this, something like this. This is a waveform. We could add another wave with a different frequency and a different amplitude. To find what these two waves would produce when they were added together, what we can do is find the sum of the two waves at various points. So for instance here, both waves are at 0, so the sum is here. About here, this wave has this value and this wave has a slightly larger value. The two would sum to about here. I can carry on at various different points along the wave. And if we now join these with a line, we get a rather complicated shape. This black line is the sum of the blue line and the red line. The spectrum is just a different way of showing the same information. On our previous slide, we had a wave with a frequency of 1 Hz and an amplitude of 2 millivolts, which we can represent with a line like this. We also had a wave with twice the frequency, i.e. 2 Hz, and half the amplitude at 1 millivolt, and we can represent that with this line. So this spectrum gives exactly the same information as the sum of the two waves we had on the previous slide. We can now easily show the bandwidth on this diagram. That would be given by this arrow. Bandwidth is the range of frequencies in a signal, or it would be the highest frequency of 2 Hz minus the lowest frequency of 1 Hz, giving a bandwidth here of 1 Hz. Any waveform can be made up of a combination of different frequencies and amplitudes of sine wave, including something like this more complicated waveform. We might find that the spectrum of that waveform is something like this, and again the bandwidth would be from the highest frequency minus the lowest frequency. If this was a radio wave, the highest amplitude here would be the carrier frequency. Radio broadcasts are encoded onto a wave called a carrier wave. This is then removed by the receiver, leaving behind just the signal. There are a limited range of frequencies available, so the number of broadcasters that can send signals is limited by the bandwidth needed for each. Radio stations are separated by a gap of at least 0.2 MHz. This is to allow each to have sufficient bandwidth and not interfere with a neighbouring broadcaster. So for example here we have several carrier wave frequencies shown, 96 MHz, 96.2 MHz and so on. The coloured bands represent the bandwidth for each station, so the 97 MHz station can use frequencies from about 96.9 to 97.1. If it went below this, it would start interfering with another radio station, using 96.8 up to around about 96.9 MHz. FM radio can be transmitted using frequencies between 30 MHz and 300 MHz, a bandwidth of 270 MHz, the highest frequency minus the lowest frequency. If each broadcaster needs 0.2 MHz of bandwidth, this gives a maximum of 270 over 0.2, which is 1350 spaces available. However, a frequency can be used again by a different group if their areas do not overlap. So for example, if a broadcaster is using a particular frequency covering this area of a patch of land, different frequencies would need to be used as their neighbours. However, we could use the frequency represented by grey here as well as here because the two areas do not overlap. This broadcaster will not have a signal strong enough to reach anywhere represented by this broadcaster, and vice versa. Moving further on, we can use the frequency represented by the green here and here, or this frequency here and here. Here we have a simple map of England and Wales, and if a broadcaster uses a certain frequency represented by green and has coverage around this region of England, we would need broadcasters using different frequencies surrounding them. However, here we could use the same frequency as is being used here. The signal used by this broadcaster will not be strong enough for any of it to reach the area represented by this broadcaster. Likewise, we could use the green frequency here and here, and this frequency here and here.